Okay, so I'm going to talk about basic principle in mathematics. I don't know how many of you got to see the schedule. Did any of you get time to see the schedule? So it's. So have you heard of what this acronym stands for? Okay. So it's a standard principle in mathematics. You must have seen this like in your high school. So can one of you state the principle? There are some pigeons and there are some holes. So
holes and n plus 1 pigeons, we have to fit such that there will be at least 2 pigeons in any one of the rooms.
you have to fit such that. So if there are 5 pigeons and there are 4 holes, there is at least one hole that has at least 2 pigeons, right? So you should not flip the pigeons and the holes around. There should be more pigeons than there are holes. So let me write that. So there is at least one hole that has at least 2 pigeons. Is that okay? Yeah, so you don't have to be a mathematician nor do you have to be an ornithologist to understand this, right? I mean, this has nothing to do with pigeons or holes. You can do this with balls, bins, anything, right? There are more objects than there are boxes, right? So this is the principle we are going to talk about today. It's a simple principle, right? So something that you understand the way it is written. So we are going to see some applications of this principle. I'm sure you have seen this in like your courses on discrete mathematics. So we are going to see this principle in ways you have not seen this before. So you might think that you know pigeonhole principle. It appears that even the statement seemed difficult to state, right? To recollect from memory. So you should not recollect from memory. There are n plus 1 pigeons, there are n holes, and there is at least one hole that has at least 2 pigeons. So we are going to see some applications of this to graph theory, number theory, geometry and so on, in places that you did not think pigeonhole principle would be used. So let me begin with some applications in graph theory. So by now I think you know what graphs are. It's a set of vertices and you have a set of edges. So maybe you should try and draw a graph with your, you can choose any number of vertices and some number of edges, where every vertex has a distinct degree. Can you do that? Maybe 5 vertices, and every vertex should have a degree that is different from every other vertex.
It's not correct only.
It's what?
It is not correct only. Difficult.
So maybe we'll say G is a simple graph, G is connected. Other assumptions that you want to make. Can you try and draw? Okay, so how do you show it's not possible? So what is the statement? In any simple graph G, there exists 2 vertices of same degree. So can you prove that? So how do you prove that? He said it's not possible, so you should be able to prove it. Can you try and give a proof? I mean, whoever said it's not possible.
For 5 vertices, the maximum number of edges it can be adjacent, it can be 4.
Okay, because the graph is simple.
Yes.
Okay.
For the degree being distinct, the possibilities are 1, 2, 3 and 4, but we have 5 vertices. So at least 1 degree is be repeated.
So there are 5 vertices, so n equal to 5. So let's say here n is number of vertices n. So if you want distinct degrees, then the numbers are 1, 2, 3, 4. I mean, you're saying suppose this is not the case. Is that what you're trying to argue? Okay. Is that it? It can be 0, right?
It's correct.
And it can be 0, but the number of degrees will be reduced. 1, 2, 3 only can be possible. If 0 is come,
0 is there, then this cannot happen. So maybe we should try it for general n. It's the same argument, but you'll have to write. Okay, so what are the pigeons? It appears that the vertices are pigeons and the boxes are possible degrees, right, or the holes. So what are possible degrees? 0, 1, 2, so on up to n minus 1. Right? So these are your holes. Right? And there are n vertices. So you are going to put a vertex v into a hole I if the degree of v is I. Okay. So vertex v I if degree of v is d is the degree, right. So there are n pigeons and there are n holes. So now what do you do?
if a vertex is put on 0, there will be not n minus 1 degree.
Correct. So suppose both 0 and n minus 1 are occupied. This is not possible, right? So u is a vertex, let's say u is in hole 0 and v is in hole n minus 1. So v being in hole n minus 1 means that the degree of v is n minus 1, right. And there are n vertices, u is one of them, right. So u should have been one of the neighbors, then u cannot be in hole 0, right. Is that okay? So what this means is that holes 0 and n minus 1 are mutually exclusive. It's not the math mutual. They mean that both cannot be simultaneously occupied, right. So now how many holes are there? You cannot say 0 to n minus 1. N minus 1 of these holes are there and n vertices are there. Both 0 and n minus 1 cannot be simultaneously occupied, right. The possible degrees are these many, but two of them cannot be simultaneously occupied, which means that the number of remaining holes is n minus 1 and there are n vertices. Does it require the graph to be connected? So in a simple graph this will hold. For the example I asked you to construct, I said simple connected. This does not require connectedness, I think. Okay. So then two holes, there is one hole with two vertices. I mean all of this is at least one hole with at least two vertices. Is that okay? That is a simple example of Pigeonhole principle. Now slightly more general example. Okay, this is about something you saw probably in your earlier talks. So G is a graph. Okay. So you must have learnt about independent set in G. Right. So can you state what an independent set is? Is it a subset of vertices? Is it a subset of edges? Okay. So you say S subset of V is an independent set if I could not hear. So if for all u comma v in S, set of mutually non-adjacent vertices. You take pairwise non-adjacent, right? You take any two vertices here, they must be non-adjacent, right? Is that okay? So you may want to find sometimes the maximum independent set. Right? If I ask you to find the minimum independent set, what can you say? Just one vertex, right? So that does not make sense. So you want to find the maximum independent set. So for every graph, you can say this is the cardinality of the maximum independent set. So we will call that the independence number. So it is the size of the maximum independent set. M is maximum, minimum does not make sense, right? Just one vertex is an independent set. Is that okay? So one more quantity is the chromatic number of a graph. So you might have come across colorings in these lectures. I'm sure. Did you come across? So proper colorings. So let me say proper vertex coloring, because in this lecture we are going to see some edge coloring. So what is a proper coloring? So vertex coloring means you are going to color the vertices with some colors. And when do you say that a coloring is proper? Should get distinct colors. Okay. Different colors. And if I ask you to proper color a graph, right, what is one idea that you would do, like brute force? It has n vertices, n colors. Right? So maximum does not make sense. Right? You have to find the minimum number of colors. Right? So chromatic number is the minimum number of colors in any proper coloring in the graph. Right? The smallest number of colors you can do, and then ensure the property that any pair of adjacent, all adjacent vertices get distinct colors. So what is a chromatic number of a complete graph? This is chi, okay. I'm writing it as x. What is the independence number of? Right. So this should sort of hint. So the larger the independence number, what can you say about the number of colors? Like intuitively. It should be small, right? There are so many independent vertices, so you can give all of them the same color. Right? They are all non-adjacent. So there are 100 vertices that are all pairwise non-adjacent, all 100 of them can get blue color and you will be fine. Right? So this means that larger the independence number, smaller the chromatic number. Right? So what is the relationship between independence number and chromatic number? Okay, so let's state that. So this is the second application. State that as a claim. Okay. So alpha of G is the independence number and chi of G is the chromatic number. Graph G. So what do you think should be the relationship? Should I fill or maybe I'll fill? So this means that alpha of G is at least n by chi of G. Okay, that's what we are trying to show. So this means that they are like inversely proportional. So how do you prove this? It's already there, like I already gave the hint. So this is a graph on n vertices. Okay, so throughout n is the number of vertices in the graph. So what this says is G is a graph on n vertices whose independence number is alpha of G and whose chromatic number is chi of G. We want to show that n can be at most the product of these two quantities. Is it clear what we want to show? It's clear, not clear? You have to try and use pigeonhole principle, right? At least that should be clear. So what is a coloring? It's giving every vertex a color. Right? So we know that G is a graph whose, okay, so what does this say? G is a graph. Alpha of G is the independence number, I don't know, independence number, and chi of G is the chromatic number.
So each color have, I mean, what is this receiving same color will be an independent.
Correct. So that is intuition. So what are the boxes and what are the holes and what are the pigeons? So different colors can be different pigeons, different holes, right? So how many such colors are there? 5 of G colors are there. So there are so many boxes. So let me put color 1, color 2. So chi of G, the chromatic number of G is chi of G, means that there exists a coloring of the vertices such that it is proper, right? And yeah, so now can you complete the argument? There are n vertices. So I am just writing. So why is this true? If all the boxes actually contained strictly less than n times chi of G many vertices, there are chi of G many such boxes, the total number of vertices strictly less than n, right? Is that okay? So there are so many boxes, so there should be at least one box that contains at least so many vertices. If that is not the case, then you are getting a fact, you are trying to show that the number of vertices in the graph itself is strictly less than n, right? But you assume, you started with this fact that the number of vertices in G is n. Is that okay? Okay. So now you have that there is at least one color class that contains so many vertices. So now what can you say?
If we take that as the maximum independence.
Okay, so what do you know about this box? So let's say that one color class is C2.
Alpha, it's independent. It's an independence.
Right, so this box has at least so many vertices and you know that all of them were given the same color, right, and the coloring was proper. So it means that these were non-adjacent vertices, right. So your maximum independent set size should be at least this much. Is that okay? This moves the lines. Is that okay? Okay, so how far can this gap be made? Something I wanted to talk about. Okay, so maybe we should try and take this example. There's 7 vertices. Okay. So this is K7 and then there are some rays. Okay, so this is called a sunlet, I think, as a name. So what is the independence number of this graph? What is the chromatic number? I mean, it looks like a sun, right? This is a complete graph and then there are some rays outside. So it's a 7 sunlet and there are 7 vertices in the center and then there are some rays. So what is the chromatic number of this? Huh? So this is a K7, so there is a complete graph sitting inside, which I haven't drawn. I mean, there are more edges. So how do you color it with 2 colors? It's not clear to me. Yeah, so K7, right? So this already requires 7 colors and then you can reuse those 7 colors for the rays, right? So, okay. Chi. What about the independence number? Oh, I messed up. Okay. Yeah. 7. Okay. What is n? N was 14. So what this gives you is actually much weaker than this example, right? So this you can generalize to a kn in the middle and then sum. Is that okay? So this tells you that the independence number is at least 2. The statement there says alpha of g is at least n by chi of g, but the actual independence number is 7. Right? So just by getting the theorem, you cannot get a good bound. This gives you some bound, right? But the bound can actually be much larger than what this theorem gives you. Is that okay? It is a somewhat not so complicated application of Pigeonhole. Okay. So now this is a theorem in extremal graph theory. So we'll see what the statement and all is. Okay. So what do we want to do? So I'm going to give you a graph, right? And I don't want the graph to have triangles. So triangle is something like this. C3 or K3. So this is what we'll call a triangle. So let's say G is a graph, right? And I want this graph to not have triangles. So how many edges can this graph have? So the idea is, if the graph has so many edges, then it is very likely that there will be a triangle. For example, K7, right? It has a triangle. Right? K4 has triangles. In fact, K4 has many triangles, right? Not just one. Right? So more the number of edges in the graph, it is very likely that there will be a triangle. Okay. So now we want to ask, if I want the graph to not have triangles, what is the maximum number of edges that can be there in the graph? If G right? Is the question clear? So maybe you can try to draw a graph on 4 vertices. 4 is a good choice, or maybe 5 vertices that does not contain a triangle. I mean, you have to estimate this quantity, so it's not clear how to estimate. I mean, maybe the outer pentagon is not there, but there are 5 vertices. So I want you to pump in as many edges as possible, but not introduce a triangle. Complete bipartite graph. Okay. So maybe totally there are 5, so I can put 3 here and 2 here. You can put in some edges in between, right? Put all possible edges in between. So how many edges will be there? Okay, so maybe n was even, right? So I'll take, n was odd, right? So let me take, so one more. Right? So if I take n, so I can take this kn, n by 2, and another kn by 2 here, right? And put all edges across. This does not have a triangle because bipartite graphs can't have odd cycles. It's no longer bipartite if there were a triangle. right? So what is the number of edges in this graph? Every vertex has n by 2 neighbors, there are n by 2 vertices, right? N square by 4. So can you add one more edge to this graph and not get a triangle? It's not possible, right? But can you construct some graph, some other graph, maybe that's not this, right, with n vertices and n square by 4 plus 1 edges that does not have a triangle? Maybe it's not this, I mean this was a clever choice, right, you wanted to avoid triangles, maybe there's some other graph. So can you construct a G, construct a G on n vertices and greater than n square by 4 edges without a triangle? So is the question clear? Yes? So can you construct? The question is clear. Did you nod for that, or did you nod for the fact that you can construct? Okay, so maybe I'll give you the answer and then we'll try to prove. So if G is a graph on n vertices that has greater than n square by 4 edges, then it will always have a triangle. Okay, so that's what we want to. So let me write the statement here. Okay. Yeah, it's just this. If G has erase some portion. So maybe I'll erase this example. So let's do this for n being even. So it's easier to explain, which means that n is some 2k for so number of vertices is even. So is it clear what we are trying to prove? Right. So I am going to start with a graph. I am going to start with the assumption that the number of vertices is even and it has a lot of edges. I have to show that there exists a triangle in it. Right. Okay, so n is 2k. So what's the number of edges? Is at least 2k whole square by 4. So it's k square by it's k square. Right. So I am going to assume that the number of edges is greater than, strictly greater than k square, or it's greater than or equal to k square plus 1. So that's what if it is even, right? So what I have to show is the same as saying if G has equal to k square plus 1 edges, then G has a triangle. I mean that's what we need to show. So if k is 1, in other words there are just 2 vertices in the graph, what can you say? If G has, okay, so let us say 2k vertices and greater than or equal to k square plus 1 edges, then G has a triangle. So suppose k equal to 1. So there are 2 vertices. So k equal to 1 means that there are 2 vertices. Yeah, so how many edges can be there? At most one edge can be there, right? So the statement is vacuously true, right? So what do you do for the next step? So I have written base case, so what should you do? So this you have to say louder. I have written base case, what should you do? You, at least that should come confidently, right? What the induction step is, that might be a problem. Okay, so induction. So what is, so let's set up the induction hypothesis. So you have to assume for k, you have to show for k plus 1, right? Sorry? You said something? You should say louder, it's okay if it is wrong. I cannot even figure out who is saying what. K vertices and 2 k vertices and k square plus 1 edges, and you have to prove for 2 times k plus 1 and at least k plus 1 the whole square plus 1 many edges. That is how induction works, right? Is it okay? Right. Okay, so if G has 2k vertices and at least k square plus 1 edges, then G has a triangle. So now we need to show induction. So for induction, you have to work with a graph that has 2 times k plus 1 many vertices, right, and at least k plus 1 the whole square plus 1 many edges. You have to show that G has a triangle. Is it okay? So if induction is not clear, you should say. That is something that is more basic than the pigeonhole principle. Right. So can we try and show that? So maybe I will erase this part of the board. Okay. Okay. Okay, so G is this graph, right? It has 2 times k plus 1 many vertices and so many edges. Some number of vertices, some number of edges. So it has many edges, so there is at least one edge, definitely. Right? I mean, there are many vertices. There are some vertices that are adjacent, some vertices that are non-adjacent, and so on. So let me pick 2 vertices. So I am going to do first step, and maybe then you should do. So there are many edges, so there is at least one edge. So this is some, these are 2 vertices that are adjacent. So then there are some remaining vertices. How many of them are there? 2k plus 1 vertices were there. So let us call this part of the graph H. I mean, together this was G. Is that okay? So X has some adjacent vertices, one of them is Y, and then there can be some other edges, other neighbors. Where will they be? In H. And Y also has some neighbor. So now what can you say? Yeah, from here on I think you should take. So is it clear? So what is the setup? So there are many edges that are adjacent, many edges are there. I have picked one edge, I have separated it, and then there is the remaining portion in the graph, right? Now X has some neighbors in H, Y also has some neighbors in H.
The neighbors are not same.
The neighbors, at the moment it appears it is not the same, but if I am able to show that there is one vertex here that is adjacent to both X and Y, then I am done. That will be a triangle, right? So that is what we need to show. I need to show that there is a common neighbor of X and Y in this graph H. So suppose H itself was very dense. So let us say that the number of edges in H was at least k square plus 1. then what can you say? So by induction there is a triangle in H, and that triangle will also be there in G. Is it okay? So not okay, you should say confidently. If it's not comfortable for you, you should say no, I don't understand, because that we cannot I cannot force you to do that, you should say. Okay. So is it okay? So if the number of edges inside this is at least k square plus 1, then H contains a triangle, and that triangle will also be surviving in G. So G also contains a triangle. So what's the other case? H does not have so many edges enough to pump in the induction hypothesis, right? So okay, so now can you try to complete the argument? So this has some number of edges, okay, less than k square plus 1. Huh?
2k plus 1.
Huh. So what is at least 2k plus 1?
Number of edges in xy plus xy, and they just do the 2k.
Correct. So the number of cross edges from this part to this part, what is it? That's what we want to count. Right? So let's count. Yeah, it's what you said. So number of cross edges. Okay, so cross edges is not the right term. Okay, so this has a meaning in graph theory. I'm just using it for this picture. Number of edges crossing from this area to this area. So how many edges are there? The graph actually from induction we know has at least so many edges, right? And the number of edges contained entirely in this was strictly less than k square plus 1, right? And there was one edge here. So this is at least k plus 1 the whole square plus 1 minus k square. I think it's okay. Okay, you should check. No. So okay, so this is the number of edges in G, this is the number of edges in H, and this is the edge xy.
Less than k square.
Did I?
Strictly net.
No, I flipped something, is it? Okay, so this is the number of edges in G.
Number of edges in H is strictly less than k square plus 1. Yeah.
Oh, so it's greater than or equal to, right? So it's okay.
That should be strictly greater.
Okay. Sorry. Yeah, I should not erase it. So you should do the arithmetic. Right? You have to solve this. I mean, there's nothing to solve. This is k square plus 2k plus 1. Right. So what will you get? You will get 2k plus 1 edges. Right. So there are at least 2k plus 1 cross edges, and there are 2k vertices. Right. So what does the pigeonhole principle tell you? There are two edges that go to the same vertex. Is that okay? So the picture is, picture could be this, but there is a W such that XW and YW are in each. So then XYW is a triangle. Is that okay? So what is the discussion about? The discussion is telling you that here is an example of a graph, okay, k n by 2 n by 2 with n square by 4 edges that did not contain a triangle, and this is the best you can do. Okay. If you add one more edge to not only this but any graph that is as dense as this, it will contain a triangle. Right. So what we are trying to do here is, this is what Mantel's theorem is with this statement. So what this does is, this is trying to estimate the number of edges in a graph that forbids a triangle. Right. Now there is nothing specific about a triangle. You should ask, what if I want to forbid a k4, a k5, a k6, or c4, a c5. In fact, you can even ask questions like, what is the maximum number of edges in any graph that forbids a graph that is isomorphic to this graph. Right? You can fix your favorite graph, maybe k4, c5, whatever, and say that this is the graph. I don't want this graph to appear in my graph. I want to construct a graph that forbids any structure that is isomorphic to this structure. Right? What is the maximum number of edges it can have? Right? So this is a theory. It is called forbidden subgraph theory. So it is what is studied in extremal graph theory. So as an exercise, what you can try to do is, instead of forbidding a triangle, you can ask what is the maximum number of edges you can have in a graph that forbids any k clique, right? There should be no k. This is k3, I mean this is also c3. This is k3, so you can ask, if I want to avoid k4, k5, k6, k7 and so on, what is the maximum number of edges? Okay. So this you should try as an exercise, use pigeonhole principle to find out the number of edges. So the idea is just similar to this. You start with some examples, right, and try to find the estimate, like what he said. When you started with this example, otherwise you could not have figured out this n square by 4, right? So you start with some example, try to construct some examples, find this estimate and then try to prove it. So this theorem is called Turan's theorem. Okay. But you should try to prove it before actually looking for the proof of Turan's theorem. So Turan's theorem is this statement with the triangle replaced by kk, right, complete graphs. Okay. So is that okay?
What was the cross edges?
So you wanted to count the number of cross edges?
Like, what was the definition of cross edges?
So by cross edges, what I meant is those edges that are adjacent to both x and y, except this edge. So this is, so the set of vertices is divided into two, right? The set of vertices of h and v minus v of h. The edges that cross from here to here, or the edges across these two sets. I called these cross edges, but cross edges has a meaning. So this is not the actual terminology. But given the picture, I think it should be clear what cross edge. So this is for x, y. So I am counting the number of cross edges, right? Total number of edges minus the edges here minus this. It should be minus. Yeah. I expected some arithmetic mistake there. Okay. Is that okay? Okay, so maybe I will. Okay, this one. Okay, so next half an hour, I will try to see some more examples. So we are going to see where exactly pigeonhole principle first appeared in mathematics. It appears something very basic statement, right? So it should have been there for a long time. I mean, there's nothing great about this statement. It's not even mathematical. It's just applied. It's used in mathematics. So we are going to talk about. This is not very convenient. Is there a way to adjust the height? Okay, so I'm going to talk a bit about number theory and then we'll see where this pigeonhole principle actually came up. Okay, so you're all familiar with numbers, right? I'm sure you're all. Okay. So what is the first set of numbers that you learnt? Natural numbers. So what are these numbers? So, and then what happened? Whole numbers. Integers, right? Okay. And then? What? So what are these? Can you define?
P by Q.
I hope this board is sufficient. Then? Okay, so many answers are there. Irrationals. Okay, yeah. Thanks. Okay. So I heard some irrational, I heard some reals, so I don't know which one to write. Shall I write reals? Irrational numbers are reals, so I think it's okay. I mean, we are going to talk about irrationals, but I will write reals. So these are numbers, I am just putting some examples, okay. So what example shall I put in reals? 5. Pi. Okay. I mean, there are other interesting things, okay. It's not this set, but pi are all there. Then?
Complex.
Is that okay? So why did you get from here? How did you get from here to here? From rationals to reals? Like it came very naturally.
That the negative square root was not defined.
No, from rational to real. What was it?
Definition of root 2.
Okay. Looks like root 2 was not defined. I mean, root 2 is not here. So you had to put in root 2, right? So there, that you cannot do with rationals. So you'll have to go to reals. And then it looked like root of -1 can't be included here, right? Because if you square a real number, you are never going to get -1. It's always positive. So you had no choice but to include it here and then close the set, you got complex, right? So I think you are equipped enough to for me to describe what I have to say. Okay, so in between someone said about irrationals, right? I think it is represented as P, but I will write irrational numbers. So what is an irrational number?
That cannot be expressed as P by Q.
So that number which is not expressible as P by Q, where P and Q are integers. Okay, so numbers. A Q not expressible. So can you give some example of irrational? Root 2 he says. So all of you agree? So how do you agree? I don't know. So why is root 2 irrational? It's not clear. So first of all, what is the value of root 2 is not clear to me. So what is root 2? Okay, I hear so many representations. So we should say sequentially.
1.4.
1 point. Okay. And then what should I write? So I don't know who said, whoever said. You said, is it? So after that what happens? Root 2 is equal to 1.414, you mean? Okay. Right. So the decimal representation of root 2 is non-terminating, non-recurring. Right? Otherwise I can tell you what root 2 is. And there is nothing specific about root 2. Right? All irrationals have decimal representations that are non-terminating and non-recurring. So you cannot write them down. But if actually someone asked you to describe root 2, how will you describe? Sorry. There is x in R. So if someone asked you what is root 4, what will you say? But this is not clear to me. It's not what is the value of x is what I asked. This is the definition of root 2, right? What is root 2? This is what you say root 2 in English or English with math. But what is the value of root 2? If someone asked you, just show me what root 2 is.
Length of hypotenuse or size of.
So maybe you should do this. This is what root 2 is. Right? So it is a bit difficult to represent it as a number. But if someone asks you what root 2 is, you can actually draw this and say that look, the side of this triangle, right angle triangle, is actually root 2. You measure it, you will get root 2. Right? So that is one geometric way of doing it. Of course, there are other irrationals, pi e. So what about pi? If someone asked you what is pi, what would you say? Pi is 3.14. So pi is 3.14 or pi is approximately 3.14. No, but what is pi like this? Circumference to and diameter, right? Yeah, these are things you have seen. I don't think I should do so much build up for rational numbers, but irrational numbers, but anyway I am doing. Okay. So this is a ratio. So why is this irrational? It's not clear.
At least one of circumference or diameter would be irrational then.
Yeah, so that is something you have to think about. Okay, it's a ratio, but it is not the ratio of two integers. No, otherwise the way I have written it looks like pi is rational. So pi, e irrational are deep statements. I am not going to show. But root 2 is irrational. Maybe you can show. So you all nodded when he said root 2 is irrational. So maybe you should say how did you get root 2 is irrational? Yeah, it's not a great proof, but I am going to demonstrate something with it. Maybe you have seen it. But so you all know that root 2 is irrational. I mean, when you know a proof.
By contradiction.
So can you try? Maybe you can. Oh, this will go up. Okay. Okay. Okay, so we are going to assume root 2 is rational. So let me put for the sake of contradiction. Okay. Just in case someone copies, then I don't want them to say root 2 is rational. So then root 2 can be written as p by q. Q non-zero. Then what happens? Okay. So p square is 2 times q square. I think that's what you asked me to do, right? Square. So what happens next? Okay, so this means that p is even, p square is even. This implies that p is even. Okay. So then what happens? So p is some 2 times, I don't know, k. So I'll substitute here. So 2k whole square is 2 times q square. Oh, sorry, this means that q square is even. Okay, is
P and Q have relative.
so there is something we did not assume, so we are trying to fix. Okay, so what this says is root 2 can be written as, I don't know, I am just writing it k by l, some other k by l, right? You started with p by q. Actually, you do not have to assume that the GCD is 1, right? You started with a p by q, you are able to represent this as k by l, right? Where k is less than p and l is less than q. So now you can apply the same argument again, and then what will happen? Smaller and smaller numbers until what happens? So it is root 2, so p and q have to be both positive integers, and q is non-zero. Is that okay? So if you try and represent root 2 as p by q, you can also represent root 2 as k by l, where k and l are smaller than p by q, I mean p and q. Now you can apply the same argument and represent root 2 as some k prime by l prime, where k prime and l prime are smaller than k and l. Okay. So this means that you are infinitely descending, right, in the chain of natural numbers, and at some point this has to stop. This is not possible, right? So an infinite descent is not possible. This is called a proof by infinite descent. So this is the simplest proof by infinite descent. There are many beautiful proofs by infinite descent. It means that you start with a property, you want to show some property holds, I mean, or does not hold. You assume it holds and says it holds also for smaller numbers. Now it can also hold for smaller numbers, and then you are working over, let's say, naturals. You can't do this. Okay. So this is what you mean by root 2 is irrational. This is how you showed root 2 is irrational. Okay. So now let me try to get to where I want. Okay. So if I want to actually approximate the value of root 2, And given that I cannot exactly tell you what root 2 is, I have to find some approximation, right? Or even pi we said is like 22 by 7 or something. You got some value for 3.14, right? So how did you get that? Huh? You said something. You should say it louder. No, you should say it's okay if it is incorrect. That is what you should learn, right? It's okay.
Root 2 we can get using long division.
Huh. So there are many methods in which you can approximate, right? So one method is like this continued fractions, which you would have learned. So do you recall what it is? How do you get a continued fraction for root 2? I mean, these are things you have seen in high school, so sure you know what it is. As 1 plus root 2 minus 1, then you multiply by root 2 plus 1 and divide by root 2 plus 1. I hope I will get it correct. Okay. Plus is it okay? It's okay, right? No, there is some issue. No, it's incorrect. 1 plus 1 by. I hope you didn't nod your head. So now what have you done? You have represented root 2 as 1 plus 1 by 1 plus root 2. Right? Now this root 2 again I can represent as 1 plus 1 by 1 plus root 2. Is that okay? Keep doing this. So depending on where you stop, you will get closer and closer to root 2. Right? Is that okay? So suppose I don't even want to substitute this root 2, just think of it. I will get something like root 2 is less than 2. Right? So you have, let me put 1 here. I know root 2 is between 1 and 2. Right? I don't know where exactly it is. Depending on where I stop, I will get closer and closer to the actual value of root 2. So suppose I don't substitute this further. So it's approximate. So what I can just say is less than. You put 1 and just say less than. Right? So you will get fractions that are closer and closer to the actual value of root 2. Well, you can never get to the original value of root 2 because this is infinite, right? If the number is actually rational, then there is a finite sequence of continued fractions. So this is one way to get to actual root. So now what we want to study is I want to approximate irrationals by rationals. Is it well, is it bad is not clear. So let me put well. What is well is also not clear at this point, right? What do you mean by approximating this? So this is what Dirichlet studied. On approximation of irrationals by rationals, people have also studied approximating reals by rationals. There is nothing to do with. And why should you only approximate pi, root 2 and so on? And approximate other real numbers also. Okay, so we should say, okay, so how do I want to approximate is not clear. So let us say that x is a real number. X can also be irrational, x can be root 2 for instance. So what do we mean by approximating x by a rational? What would you think it would be? So x is real, let us say x is irrational. So x you cannot write as p by q. Right? But what do you mean by approximating x by p by q?
Some p by q is close enough to x.
That is close enough to x. Right? So what is close enough mean here? What should close enough mean?
You can define some error, that's okay.
Okay, so x minus p by q. Let me take the absolute value, the easiest. So you want to find a p by q that is closest to x in absolute value. Then this is what you mean approximating x, which is irrational by rational. Okay. So I want to say that for every x, right, and maybe I should say, so I want to approximate it well, meaning that I have to choose how close it is to x. Okay. So if I tell you that I want to be this close to x, right, can you give me a p such that x minus p by q is less than 1 by q? So for every x in R and for every q, there is no space, I should write, there exists a p. Right? In fact, I can say natural numbers, but is that okay? So what I am trying to say is that for every real number, right, you choose how close you want to be, and I will give you a p such that p by q is that close. I have used some English terms, that close, how close, and so on, but it should be. Is that okay? So this is a measure of closeness, the first measure. So this is something we want to show, it's a claim. For every real number and for every choice of denominator, there is a choice of numerator, right, such that the absolute value between x and the rational number is at most 1 by q. So you can get really close, right, you can choose the q and I will give you a p. Is that okay? So shall we try a proof of this? So how do you think we should? So x is a real number, it is somewhere on the real line. So for now let me assume that it is between 0 and 1. Okay. I mean it does not have to be between 0 and so maybe it is not required, yeah, it is fine. So let me say it is positive, maybe it is greater than or equal to 0. I mean the proof does not require it, I am just doing it so that it is easy. Okay. So can you try and see how to get this? So I have given you a q also, you have to give me a p. Is it clear what we are trying to do? So x is fixed, q is given, we have to find a p such that the difference of the absolute value is at most 1 by q, strictly less than 1 by q. I have told 1 by q is all that you can, all how close you want to get. So what should you do? So let us say x is greater than 0, it can be less than 0 at all, can be equal to 0. So you have 0, let me put 1 by q, to 2 by q. So I am going to divide the real line into intervals like this. So 0, 1 by q, 1 by q, 2 by q, 2 by q. So I have done half the job. Now can you say how to approximate? So x is a real number, x is exactly in one of the intervals, right? So x is in c by q and c plus 1 by q for some c. So what is your p? This qx minus 1 is not clear to me. Okay, I don't know, let me write what he is saying. P is, oh, there is no c, I am a bit confused. How did you get this? Can you say? It is not clear to me. No.
Taking the modulus of
No, so it is not clear to me. So what are we trying to show? Maybe you missed the point. I mean one of us missed the point, I am trying to figure out who. So what I want to do is come up with a p, right. So if I fix p to be qx minus 1, It is strange. This is the same as C plus 1, right? Is it not? Okay, you're just saying that take P equal to QX minus 1.
If we take x minus p by q equal to 1 by q, then we get
You just get 1 by q.
So you will get 1 by Q, right? Not less than 1 by Q. You have to go strictly less than 1 by Q. Yeah, so if it's equal to 1 by Q, it is trivial, I think. That's what you mean. I mean, even strictly less than seems. So you choose P to be C plus 1, right? The length of the interval is strictly less than 1 by Q, right? So its absolute value has to be less than 1 by Q. This did not use pigeonhole principle, by the way. Right? We did nothing. You just divided the real line into intervals and said that this real number has to be somewhere in one of the intervals. The length of the interval itself I cheated by saying it is less than 1 by Q, so it has to be closer to a rational number. I mean, whatever is the next rational number in this interval representation of the real line, that is the numerator. Is that okay? So I have gotten closer to this real number, which is also maybe possibly rational, by a factor of 1 by Q, right, by doing this without using pigeonhole principle. So what would you expect if I use pigeonhole principle?
So we can make boxes as these intervals as boxes and the balls as that n plus 1 boxes. The one we are approximating. X and
But there is only one number that you are approximating, so it is not clear to me. There are many boxes and then there is one. Yeah, it looks like something like that, right? Some pigeon should be there, some hole should be there. It's not clear what is the pigeon and what is the hole. Also, if you do this, I think there are infinitely many boxes, right? This is the whole real line. Okay, so some PHP we have to use, that's what we'll do. And by doing that, you should be able to improve the approximation. That is the point, right? You are using some substantial principle that is not just this. So you should get a better approximation by applying PHP. Okay, so what is that better? So let me write that. For any positive rings. Okay, so maybe realism. And for all Q. This. So I have improved this 1 by Q to 1 by Q square. So it's not.
Taken alpha is in R.
Okay, so I think the proof that I'll say is going to. Okay, so maybe I'll put plus. So these statements are not limited to positives, okay? So I'm just using positive because it's easy to draw. Well, you can also extend it this side.
You can assume that it's between 0 and 1.
You can assume it is between 0 and 1, that's what we are going to do. So let's assume it is between 0 and 1, maybe. I don't know if 0 should be included, maybe not, I'll include 0. For simplicity, okay, so all of this is for simplicity. The statements are all very general. So is the statement clear? Is the same approximation measure, but from 1 by Q I have gone to 1 by Q square by using pigeonhole principle, right? So now maybe we can try what he said. It's a real number, so what can you do? So I'll put 0 to 1. I put 0 to 1 so that that box business is easy. So alpha is some real number. So how will alpha be represented? It has something here plus some. I mean not plus, times. Right. There are some digits after the decimal point. Right. So what is this? This has a name. Okay, it's 0, but floor of alpha, right? I mean here it is 0. In general it's the floor. right? Whatever is the smallest integer close, largest integer close. And this is the fractional part of alpha, right? So I am going to give it some notation. Yes. Right? So this alpha is actually, is that okay? It's okay. There is some notation, okay, for me to write, so it's easier to write. So let's do what he suggested, the same business here. So I included 0, these two should 0, 1 by q, 1 by q, 2 by q, and how far can I go? Okay, so these are closed intervals, these are open. I started with left closed, right open. Until what?
Q by Q, Q by Q.
So 1 is q by q. So what should the one before it be?
Q minus 1 by Q.
So the intervals are 0, 1 by q, 1 by q, 2 by q, to q minus 1 by q and 1. Is that okay? Oh, I hope I didn't mess up. So what are these supposed to be? Looks like there are some. Huh? These are supposed to be pigeons? Holes, okay. Yeah, you should say completely, I cannot hear. So what should the pigeon be? What should the pigeons be? Not pigeon. There should be many pigeons. Appears that there is only one number we are trying to fit in here. It's a problem. So what can you do? You have to create some pigeons, right? So there are q holes, q, right? There are q holes. I have to create q plus 1 pigeons somehow, right? And I have one number alpha. This is the fractional part, right? So this is this part, the one after the decimal representation. So what can I do? Oh, I need, so maybe I will take, I don't know if it's okay to take 1 to q plus 1, I think it's fine. Just multiplying and taking the fractional part. So there are q plus 1 pigeons, there are q holes. The pigeons have something to do with alpha, it's not exactly alpha, right? Okay. So what will you do? What will you get if you apply pigeonhole principle now?
There is a particular interval where you'll have two of those.
Two of these will be there in one of the boxes, right? So there is, maybe I'll give it a name, I think it's okay. Okay, so there are two things, let me call it L alpha and K alpha. I mean, it's not important. So this is the maximum. These are in the same interval, right? Two of them. Is that okay? By now you should have guessed what is going on. So what is this? L alpha okay. Is that okay? So how far can these two things be in absolute value? So they are in the same box, and what is the length of the box? No, so L alpha and K alpha are both on this, both in this interval, and each of them has length less than 1 by q, right? Is it okay? So this is clear, right, from PHP. So if it's not clear, you should say, okay, I cannot look at everyone's face and detect. Right, so now I know what L alpha and K alpha are, so I can substitute. So now can you complete? I have done most of it.
If you are assuming 0 to 1, we need not think of that.
Yeah, you can actually think of this as 0, right? Yeah, that is true. So what did we want to do? Maybe we can just go back and see, right? So Q was given to us, we have to figure out the P, right? So what is the P? So can you tell me what the P is from here? It's already in that representation almost. So maybe I will divide by L minus K. Q, is that okay? So now what is P, what is Q?
You will have to divide.
Okay. Yeah. So this is gone, I mean gone meaning this is 1, okay. So this is alpha minus P by Q, right? And then what, I mean how far can L and K be? So what are L and K? So L is between 1, 2, so on up to Q plus 1, K is between 1, 2, so on up to Q plus 1. They can be Q apart, right? So this is less than 1 by Q square, right? And this is alpha minus P by Q. Right?
L minus K.
Where should it be L minus K? Q should be L minus K, is it? Why is it?
Have L minus K. But I think that's fine.
This inequality is fine, right? Is there a problem? Maybe there is a issue. Don't think there is a problem. So
Q is big. What's P?
so P is so P I thought is L alpha minus K alpha. Okay, but there is some problem. I have to represent this in terms of Q, right? Yeah, I think so. I mean, I should represent P as a function of Q, right? Yeah. Okay, so what this says is something slightly different. This says for any alpha there is a P and a Q. The statement I wanted is slightly different, right? For every alpha, for every Q there should be a P.
For every Q, there is a.
There is, okay, but I don't know how to write. Maybe there is. Okay, give me 1 second. Should write exactly what Q is, right?
You just want that most denominator
Right. So
in terms of like an approximation, that is good. Like that.
so if P is this and Q is this, then alpha minus P by Q, where alpha is the given real number, is less than 1 by Q square. Right? So this statement is fine. It's just that it will not be exactly Q. Okay. Don't think that's a problem. Not sure if I have to change the statement. So the statement of Dirichlet's theorem is this. Okay, so I don't want to change that statement. Okay, so what I wanted to say is, okay, I may have to fix this. I'm not sure. Okay, but at least you have used pigeonhole principle to get a better approximation of reals by rationals. So pigeonhole principle was, this was the first place where pigeonhole principle was used. It is called Dirichlet's box principle. At least in literature, this is the first place where it was used. Maybe it got pigeonhole names later on, but the first place where it was used is to approximate reals by rationals. So now this Q square here, you can improve it to root 5 times Q square. Okay. So this is by Hurwitz. Okay, so and you cannot improve it beyond a certain point. So you cannot get a constant that is better than root 5 here. So that is also something we know. You can improve it, but there is only some limit to which you can improve it. Okay? So you cannot keep improving it. So one work that studies how far you can approximate irrationals by rationals or reals by rationals, right? How close can you get to them is Roth's theorem. And these are things you can go back and look up if you want to. So they got the Fields Medal for this. It's equivalent to the Nobel Prize in mathematics, right? It looks like a simple statement. Showing this is easy, but showing that you cannot approximate beyond the limit, right? That is hard. So you want, for such a statement to hold, you would want to say that there is an alpha such that no matter what rational numbers you choose, you cannot approximate beyond this, right? It's like the complement statement of what is written here. Here we are given alpha and you are trying to approximate it for every alpha, right? Okay, so that is one application of pigeonhole principle in number theory. Okay, so now I should do something else. We have 5 minutes. Let's see. So I'll do something simple in 5 minutes and maybe we'll do more stuff tomorrow. Okay, I'll erase this. Is that okay? Okay. So you must have heard of data compression, right? So can you describe what it is? I mean in English. Reducing the size of the data. Okay. Like without losing the actual content, right? So that's what he says. Is it agreeable? Right. So let's say you have n bits of information, right? So let's say Alice has n bits of information and wants to transmit it to Bob on some channel, but I am going to say that the channel can only accommodate n minus 1 bits. Okay. So now the goal for Alice is to send these n bits of information using n minus 1 bits in a way that Bob can actually retrieve the original message, right? Is that okay? So in data compression you have a compression function, right? C. So it maps, let's say, n bit strings to n minus 1 bit strings. So I have written n minus 1. Ideally what you want to do is on k bits where k is much smaller than n, you do not have bandwidth for so much bits, right? And you want a decompress function that Bob has to apply, right? So this is from 0 1 to n minus 1, whatever she has received, to 0 1 to the n, such that if you look at x and apply compress and then apply decompress, you should get x, right? So decompress is an inverse function of compress. That is what data compression is supposed to do, right? If it is lossless, like your zip, you are given a file, you are going to compress it, right, without losing any information about the file. Okay. So can we do this? That is what we want to ask. So suppose we were able to do this, what will happen? Can you try to see what is going on? So the total possible messages are bit strings of length n, right? These are strings of length n. So let me say at most n minus 1, okay. You can do 1 bit, 2 bits, well, maybe you are just say using 2 bits. The communication channel has a capacity that is n minus 1. So you can use fewer than that also if you are intelligent. So how many possible input messages can Alice generate? So there are 2 power n messages This is Alice's message world, right? And she is going to say that, okay, right? She is going to say that if I see x, I am going to transmit it as some y, which has length less than n. If I see an x prime, I am going to possibly transmit it as a y prime, which also has length less than n, right? So, what are possible communications that she can do? So, this is the actual message, this is what she is going to communicate. So, that is also some set, let me put less than n, all possible strings of length less than n. Right? Maybe if she sees all 0, she will send just 0. If she sees all 1, she will send just 1. It's something like that. She is going to do some algorithm. We have no idea on what algorithm she is going to apply. But the only thing she will do is she will take the string of length n and she will do apply some function which is the compression function and then send a string which has length less than n. Right? So, how many possible strings are there? Right? So many possible communications. These are possible communication messages, these are actual messages. So, now what can happen? So, what does this tell you? I mean, these are possible messages she can send. These are the possible messages she wants to send and these are the possible messages she can send on the channel. Can she? So, there are 2 to the n of them. This is 2 to the n minus 1 of the possible communications. Or maybe you can think of this as letters. I mean, she wants to convey this message, she is writing a letter. So, what is not clear? So, let us see. So, Alice, let us say, has some string that she wants to communicate. So, let me put 0 1 0 0 1 0. Okay. So, this let us say has n bits. She wants to communicate this using at most n minus 1 bits, and she cannot communicate n bits, that channel is only n minus 1 bits long. So, maybe she will map this to maybe drop the first 0. She can do anything, I am just saying suppose she does this, and this is the compress function. Now, Bob has to figure out from this string whether the actual string was 0 1 0 0 or 1 1, right? Does this seem possible? That is a question. Can she do this? Who said yes? Someone said yes. So, then someone said no. I heard something, so it should be only yes or no. So, there are 2 to the n possible messages that she wants to send. There are 2 to the n minus 1 possible messages she can send. So, if you apply PHP, what do you get?
At least one thing will have two.
At least 2 things will have the same encoding, right? So, there are 2 messages x and y, or maybe x and x prime, that get mapped to y. Now, Bob, by looking at y, cannot distinguish whether it was x or x prime, right? Is that okay? So, what does this say?
You can only send two possible distinct messages.
Correct. So, what this says is perfect lossless data compression is impossible. This just says that you cannot communicate n bits of information using n minus 1 bits. Right? It is not possible. It is a limit on how much you can communicate. You have to use at least n bits. Maybe you can do cleverer things. Right? If there are some patterns or structure in the data, then you can do much better things. For example, you are promised that the given file will have a header where the first 1000 bits are going to be 0. And Alice and Bob both know this. Then you can do all this. If the message can be completely arbitrary, any one of the 2 to the n possible bit strings, then it is not possible to perfectly lossless compress data and send it on a communication channel that is lesser than n bits long. Right? So, all our lossless data compression algorithms, zip and those things use the fact that this data has some structure, the file has some structure. it has a header, it has a footer. So those things are known, right, if it's a PDF and so on. Right. So this is the first building block to this area which is called information theory. So this was studied by Shannon. Must have heard of Shannon, Claude Shannon. Right. It's a scientist who discovered information theory. So it is a theory of how information can be reliably transmitted, right, how to transmit data reliably, effectively without these kind of things. And there are some limits to how much information you can transmit using these many bits. Right. That's what Shannon's information theory studies. Okay. So yeah, it's a very nice paper you can read. It's called A Mathematical Theory of Communication. It's a very old paper, but something that everyone can read. Yeah, Shannon was working in Bell Labs, I think. Shannon, Hamming. So they are people who discovered information theory at the time when actually we were sending information on channels, physical channels. Right? Okay, so this is where information theory uses pigeon. It's a very simple example of pigeonhole principle being used in information theory. Okay, so there are some more examples which we'll see maybe tomorrow. Coloring, Ramsey theory and so on. Right, and one example in computational geometry. Okay, so that is all.